We're in Rosen, Discrete Mathematics and its Applications, Section 2.3 on Functions. We're going to discuss two important functions for this course and other uses of this textbook. Those are the floor function and the ceiling function. We have the definition of the floor function at the top of this graph, or this slide, and the floor function is denoted with an X and a bracket around it with missing the top piece. So X with this little walls and two floors but no ceiling. And it is the largest integer less than or equal to X, where X is usually a real number. And the ceiling function, so there's the floor piece. The ceiling function, notice it has two walls and sort of a ceiling but no floor, is similar, but it is the smallest integer that is greater than or equal to X. So that the ceiling function of 3.5 will be 4, and the floor function of 3.5 will be 3. Note that the negatives, we have to be a little bit careful. The ceiling of negative 1.5 is negative 1, because negative 1 is greater than negative 1.5. And the floor of negative 1.5 is negative 2, since it is less than negative 1.5. Okay. This slide, we have a graph of it. Small error here. So this is the floor function. So this is going to be X floor function. This is the ceiling function. So this will be X ceiling function. So here's X, here's f of X, X, f of X. And whenever X is between 0 and 1, not inclusive of 1, we return 0. Whenever X is between 1 and 2, not inclusive of 2, we get 1, and so forth. So these graphs look the same except they're shifted up in the case of the ceiling function. Some important properties of the ceiling functions and floor functions. The floor function of x, a real number, is equal to n if and only if x is between n and n plus 1 inclusive of n. And the ceiling function of x is equal to n if and only if x is between n minus 1 and n inclusive of n. You could derive these next two from the first two, where the floor function of x is equal to n if and only if x minus n is between x minus 1 and x inclusive of x, and the ceiling function of x is equal to n if and only if n is between x and x plus 1 inclusive of x. Notably that x minus 1 is strictly less than the floor function, which is less than or equal to x, which is less than or equal to the ceiling function, which is strictly less than x plus 1. Note that the floor function of the negative is equal to the negative of the ceiling function. And the ceiling function of the negative is equal to the negative of the floor function. You could look at our prior example with negative 1.5 to illustrate that. And finally, the floor function of x plus an integer is equal to the quantity is equal to the floor function of x plus the integer. And the floor function of the ceiling function of x plus an integer is equal to the ceiling function of x plus that same integer. We're going to do a proof of a proposition using floor functions. Here I have 2x is the floor function of 2x is equal to x plus the floor function of x plus the floor function of x plus a half. So say that again. Floor function of 2x is equal to the floor function of x plus the floor function of x plus a half. All right, we'll do it in two cases. First, we'll say that x is equal to n plus epsilon, where n is an integer and epsilon is a real fraction between 0 and 1, inclusive of 0. So when epsilon is 0, then x is equal to n. And we'll have two cases, one where epsilon is strictly less than 1/2. And the nice thing about this assumption is that twice epsilon will be strictly less than 1. All right, first let's take a look at the 2x portion of our equation. Since 2x is equal to 2n plus 2 epsilon, and I just mentioned that 2 epsilon will be strictly less than 1, then the floor function of 2x will equal to 2n. All right, and since the floor function of x plus 1/2 will also equal to n, because since epsilon is strictly less than 1/2, then epsilon plus 1/2 is strictly less than 1, and so the floor function of x will equal, x plus 1/2 will equal to n. And now we can combine them all together. We already know that the floor function of x is equal to n, so since the floor function of 2x is 2n, and the floor function of x plus 1/2 is equal to n plus n, which is 2n, it works for the first case. Now let's take the remainder, the second case, which will be epsilon greater than or equal to 1/2. And remember, it'll still be strictly less than 1. All right. So let's take 2x again. If we have 2n plus 2 epsilon, and if I add and subtract a 1 to this, I get 2n plus 1 and 2 epsilon minus 1. But 2 epsilon minus 1, so since epsilon is greater than or equal to 1/2, then 2 epsilon minus 1 will be between 0 and 1. And so the floor function of 2x will be 2n plus 1. And now let's take a look at x plus 1/2. Since x plus 1/2 is equal to n plus 1/2 plus epsilon, I can add and subtract a half. So I'll get n plus 1 plus epsilon minus 1/2. And we know that epsilon minus 1/2 will be between 0 and 1, so the floor function of x plus 1/2 will equal to n plus 1. And I'll combine those all to get 2x is 2n plus 1. The floor function of x plus the floor function of x plus 1/2 is n plus 1, which is also 2n plus 1. And we've proven it for the second and all of the cases. So it is so this proposition is proven.